Thank you very much for coming to this talk. Thank you for inviting me to this workshop as well. Today I'll be talking about holistic urban modeling, and more precisely capturing and designing the form and function of urban space. So this project has as a goal providing what-if urban tools that enable a variety of urban stakeholders worldwide to automatically integrate, process, analyze, and visualize form and function related to urban spaces. And urban spaces are very good examples of holistic scene structures because they're man-made. There is a good amount of repetition, design, and form rules that we can take advantage of to improve this task. And in particular, we've been using methods in computer vision as well as computer graphics to understand this holistic scene structure, as well as the interdependencies between the form, the function, and the environment. So our project is in fact a multidisciplinary adventure, and we've been collaborating with people, of course, within computer science, but also outside, such as in architecture and urban design, atmospheric sciences, engineering, earth sciences, hydrology, meteorology, and urban planning. And this has been a project that has involved a large number of contributors over the years. We've been doing this for about this particular type of research for about 10 plus years, maybe 12 years by now, and we're still going strong, and many students and collaborators have worked in our projects. So I'm not only going to be talking today about work that we've done, but also work that I've done together with my students and collaborators over the years. So it's not just me. So first, cities. What are cities? Well, at first, cities were rather simple structures like these nomad huts of the past. Then as civilization progressed, started making more permanent structures, such as here in Jordan, houses or buildings inside mountains. And also in South America, they made cities on top of mountains as well. But today, cities are very complicated structures with many more rules and patterns and a very complicated urban ecosystem, such as here in Chicago, New York, or Riyadh. Cities are house a large number of people, much vehicles, power consumption, waste production, and they're also the mecca for some architectural projects, such as these here, the city of Singapore here and its structures. You can see, like for example, the rooftop green and parks on top there of the building. So cities have come about because there is a huge world population. You can see here pretty much in the last few hundred years, the population has grown tremendously. And we're about 7 billion people now, and we are going to reach even more in the next few decades. Unfortunately, this junction of many people and the large and, so to speak, complicated urban needs create problems, such as, for example, an uncontrolled horizontal urban sprawl, just structures appearing horizontally in a disorganized way. And here we can see other examples in Asia. Also brings lots of traffic, either public transportation or private transportation, causing traffic jams and delays of going from one part of the city to the other. And of course, all this traffic brings pollutants and greenhouse gases that can suddenly appear and be very problematic, very unhealthy for the inhabitants of the city. And then, of course, there's waste production. Cities produce waste. And this is something we must constantly deal with, of where to put this waste, how to, in an eco and environmentally friendly way, dispose of this waste. There's also problems which are related to urban meteorology. So sudden lightning storms, tornadoes, flash flooding, hailstorms. These are exacerbated by the urban heat effect and by these man-made structures which disturb the local environment, reducing, for example, the abundance of pervious surfaces. Therefore, when rainwater comes, suddenly it might flood the city. While I could keep talking about properties about cities, and it's a really exciting topic, we've been looking at this for a while. Here's one book I really like by Michael Beatty, talks about cities and complexity. It kind of portrays cities as these complex structures that are, in a sense, like live, complicated beings. And they have some various ways which you could express the behavior. So you can look at this book and many other ones similar to it if you want to read more about cities. So in some of our applications that we've been working on, which I'll show you some of them to give you an idea what we mean by we want to understand the urban form and function, is, for example, we provide this what if tool that enables a urban stakeholder to see what is the effect of greening. So if we could, play God in this example here, we could green the upper northwest corner of Indianapolis. So this is actual model built by wonderful tools that actually capture the urban structure, population, and the employment and residential distribution in Indianapolis. And we were to green the upper left-hand corner and take those people and redistribute them elsewhere in the city. The result would be this. Even though we must consider the whole region, some weather front coming through the entire region, we see that this greening process would actually warm the city by about 1 degree centigrade on average, which is considerable. On the other hand, we were to green the southeast corner, as you see in this bottom row simulation, the city, in fact, in that same weather front would get cooler. And this can be explained by the direction of the winds, whether it's upwind and downwind. So how we green the city affects how the weather can be over the city in some given weather front that comes in. So we might want to take greening into consideration when we design or allow a city to evolve over time. We don't necessarily need to, we're not advocating destroying a corner of the city and replacing trees. We're just providing tools to design this to produce hot or cool cities. Maybe you want to promote the existence of a green area around the city, or have distributed, maintain some sort of distribution of green areas inside the city. This would be another application of this what if design tool that has made use of our modeling of the holistic urban structures, which I'll talk about. More recently, another work here where we focused a little more on cloud control. So here we incorporate a meteorological simulation running on a GPU that intertwines with the urban structure that's recovered from a variety of sources. So in this what if tool, for example, the top row, the user can say, gee, I would like the cloud cover to be overcast in the morning, sun in the afternoon, and mildly cloudy in the afternoon, late afternoon. That produces the top row. So here we modulate the city structure so as to obtain this behavior. And here's 3 different examples of things that are possible by modulating the city structure. So here, this is not with regards to greening, but with regards to cloud control. Another similar to one is urban temperature. So several such efforts are in fact going on because this is actually a little more doable. We might want to change the roofs of the urban structure. Maybe make them green. In this case, we made them white. And that tends to reflect some of the sunlight or the energy back up in the atmosphere. And we also distribute some parks. So we see here different playoffs between adding only white roofs or adding only parks or adding both. And this can also reduce the temperature of the city by altering where parks are and how many white roofs are there. So this is another example of a what if planning tool that makes use of the holistic system. We've also looked at urban traffic. So here we see a nice animation of traffic through a hypothetical city. And what we did with this tool is we enabled the user to paint how they would like the traffic of the city to change and then we propose an alteration of the urban design. So here we took a model that we created from a variety of sources of Manhattan, so southern part of New York City. And we have a rough approximation of jobs and distribution of population. And with this, we're able to kind of make a trip ticket, a traffic simulation. It turns out that for these people to go from houses to work in this area, and maybe it's a travel time of about an hour, producing about 1,000 grams of carbon monoxide. So we wanted to figure out how could we reduce this time. So with the system, we're able to propose ways of changing the direction of lanes of traffic. In this case, 52 lanes. If we just change the direction that the traffic flows, we're able, in fact, to reduce the average travel time and also the carbon monoxide production. And then if we further change some lanes and we redistribute where people work, people live, we can also further reduce travel time as well as carbon monoxide. And here's a third example. That allows us to roughly half the travel time in carbon monoxide production. So again, this is a what-if tool of how we can explore different urban designs and how they affect a simulated traffic. Also, and finally, we also looked at urban flooding. So here we created these holistic models of cities, and we played with how certain design parameters of a city can affect and improve flooding in a passive way. So flooding might occur due to heavy rains or rivers nearby. And of course, there are active flooding mechanisms, and that's fine. But also people like to have passive flooding mechanisms. How can we design a city to be more robust and to less conducive to flooding occurring? So here we create a virtual city with some parameters that we can control, like parcel area, the ratio of parks, building setbacks, number of floors, road length, orientation, curvature, and width. And these are design parameters. And maybe as we grow a city, what we can do is we can promote certain values for these parameters. And with this tool, we can then study how this would affect flooding. So we created a simulation system that takes in some design parameters. We take in a representation, again, using some holistic urban structure from some existing city, and we're able to change it in some way. Then we have a porosity-based hydraulic model, which simulates flooding through the city, and then we perform some analysis, and we do this with this is actually a deep learning mini simulation system that then trains and learns how the parameters affected by urban structures. So in particular, here we see a correlation between the urban structures, the urban parameters, and flooding that's produced. So for instance, we see that building coverage is the prime parameter that affects how much flooding affects the urban area. Finally, we see here the second set of parameters, and they have different varying correlations that you can see, with perhaps the second most dominant one being a building side setback. And we are also pioneering members of this group called WUDAP. There's a website you're welcome to go to. We're trying to collect information from cities worldwide and provide tools of how we can then use this data to perform a variety of what-if scenarios. So in our particular case, we are gearing this for kind of a wide distribution. So not necessarily all cities have a very large budget they can devote to urban planning. So we want to provide tools that enable them to then do these analysis of what-if scenarios using the data that's online and tools that are hopefully online. So this is a growing project, and I could talk more about this afterwards if you like, but you're welcome to go to the website. There's a portal there with some data, and that's actually things that we host in our lab. But I said this is a grassroots effort. Here's the website. So what we do, our holistic urban modeling, we consider to be, for these applications I mentioned, we're here at the cross point between urban simulation, 3D modeling and generation from computer vision, computer graphics, and we make use of real-world data acquisition. And in particular, we've done a variety of projects that span different scales of structures, going from buildings all the way to city scale, and also varying the amount of prior information we assume that we know. From knowing very little to knowing a rather decent amount of information about the urban organization, the urban structure. So I don't have time to go through all of these projects. I'm just going to focus here today on these two extremes, city scale projects and building scale projects, both assuming not very much, so low prior assumption. So our first project we'll talk about is a satellite to city generation. So the goal is to reconstruct cities from minimal observations by satellite, exploiting some statistical features that we can deduce from the city, and ultimately generate some form of a procedural model, which we can then use for these what-if scenarios and do potential changes to the city at different scales. So we have several input to the system. Our first input uses land scan data. This is one of two major kind of world scale population data sources that are available. So using satellite and some other processing, this is produced by ORNL, and they per pixel provide a rough estimation of people that's living there. I think it's at maybe 30-meter resolution is this product. We also make use of a world level elevation, use particular this product from the Japanese Aerospace Agency that gives some rough estimate of per pixel elevation around the world. And we can use this to infer roughly a building height information. Finally, we also make use of segmented satellite information, where we segment out building structures from non-building structures. So we have this pipeline, and I'll just very quickly go over this. We take in this information, we estimate the presence of parcels. The parcels are not actually visible, but we use this as the interim structure. And from this structure, we then estimate building size using consideration population, the rough structure, setback information, and elevation. And then we have an optimization process and ultimately output a procedural model. So this parcel estimator is trained, uses a neural network, is trained using some ground truth information for several cities worldwide. And from a very rough observation of buildings, like you see here in this, this zoom in of the black buildings and white background, we try to estimate where is the lot of land, the parcel boundary, but it was not visible. And from these estimated parcel boundary, we then use statistical information about the setbacks, so how setback or structures inside the parcel, and then we get a building generator that then, based on the footprint which we observe from satellite imagery, this parcel estimation, the setback information, the building height elevation, as well as an estimation of the population, we determine one of 6 urban types, and we create a model for that which we render. So these 6 urban types here come from a global classification that's called LCZ, local climate zones. This was done by people in the urban planning and urban meteorology world. So roughly there is 10 types of urban zones across the world, and we support 6 of them. The ones missing are things like we don't support industry and other structures which are less common. These are the major structures. And these local climate zones give us a macroscopic view on the configuration of those cities. It doesn't give us exact per building structures, but it tells us the type of structures that are there. So we classify type of structures into one of these 6, and furthermore create a plausible building for each parcel that we observe. And then we have this calibration process where we assume we know a few percent of the known building area, maybe about 5%. And the building area, what we mean by that is a weighted sum of building area and building count. And then here we have 8 cities around the world. You can see the initial and the post optimization error that we obtain. And you know, it's maybe about 5%, 10% error on average after this optimization. of getting the building area and the building counts right. So we can see some top-down views here. This is Chicago. On the left is actually our result for Chicago. On the right is just for comparison. We graph from Google Earth and an aerial view. Notice that with the aerial Google Earth and Google Earth here is using actually much higher resolution aerial image to do the 3D reconstruction. We're doing this approximately 1 meter satellite. And here is New Orleans. You can see also some comparative structures. Here's Dublin and some comparisons. And here's a short little video to give you a better idea of the 3D quality. Like, remember, what we're obtaining here is a rough 3D structure that is statistically similar to reality. It's not actually metrically accurate. Every building is correct, but the type and size of buildings per city block are roughly correct. And that's this, what we call the satellite city, and a holistic at a large scale as well. Another effort, this was a city scale building generation problem. It's actually a team effort between several universities, ETH, UNC, and a company called AOA, and ourselves. And there was multiple phases of this very large pipeline. Here, the objective was to construct the most metrically accurate structures possible using the latest satellite around worldview 3.3 meters. So that was rectified and segmented and multi-view stereo and data fusion, and then the geometric modeling part. And I won't talk about all of these parts, but the green box is what we focused on. And so we got these multi-view stereo structures, and we output these very clean models you can see here, which could be used for buildings anywhere in the world. And here showing you some rather complicated examples, and no manual intervention was all automatically created. Here's some more examples, and we have a paper coming out in a month about this. The next step is a facade generation. So this is on the right is some example of the actual facades look like from 0.3 meter worldview data. So they're not, you can see the best representation, very different than street view, but yet we made a system to convert this into crisp facades. And in fact, it's a paper that's appearing here at ECCV this year, on Tuesday, I believe. Here we see some more close-ups. So here are the geometric structures which we obtained with the prior work I mentioned, multi-view viewer to crisp geometry. And then we see some comparisons, like on the left here, we see this is what the satellite imagery produces. And then we use here a deep learning optimization-based scheme that obtains this representation here on the other building for each pair that kind of sees the underlying pattern and regenerates in a synthetic way, and of course without the occlusion by the trees. Here on the right is some other examples. Here is some more city views, several buildings. We can see, and we compare this to Google Earth. You know, Google Earth is actually aerial view and very different imagery. We're doing this from the satellite structures. So if you're excited about this work, I encourage you to go to our paper on Tuesday, tell you more details about this. Another work we did was to go from urban indicators to city generation. So here, we're given a procedural model, perhaps the output of one of these prior methods or some other method, and we want to alter the city in some way to generate a variation of city that obeys certain behaviors of indicator values. So here we have procedural models. We use an optimization system, an interactive system with a GUI. There's a loop here, and there's a middle engine here. Gets eventually replaced with a neural network. So I'll give you an example here. Say we want to regulate sun exposure. So that means that what's the total amount of sun exposed to every face of a building during the course of the day, hours of sun the building receives per day, and then this over the year, beneficial for solar panels, natural light, and so forth. So this is one urban structure, and we color coding here how much sun each facade is receiving. And then if we want to alter it, if we, for instance, introduce parks and a little more spacing between buildings, it gets to have more sun exposure. And if we increase even more the spacing between buildings, of course, we get even more exposure. So this is a tool which is the output of the previous and is how we could change it for some what if scenario tools. We can also change distance to parks and floor area ratios. Another example here of how we can get kind of like very tall, high shadow structures, maybe like happens in Hong Kong, as opposed to here on the right, more like suburban towns, lower structures and wider spaces. So just to show you how the design parameters change, we show them in bar using a bar graph style representation. It's not like we're just changing a single parameter. We have to discover how to alter the procedural parameters to produce this. So here we're showing you a subset. It's about 7 of the 10 or so parameters that are changed here. And some of these are spatially varying. So it's not like a global parameter, but they change with every grid cell in this design area. And here's a more complicated example that we actually, one of my students was in fact hired to do this, to design an area in Bangladesh. So that's at the city scale. Let me talk now a little bit about things at the building scale. So this is one work we did where we go from sketching to procedural models. So the user sketches things with their hand using a tablet and using a neural network system. They would then generate a building which we can render using nice computer graphics. So there's an offline training part and an online sketching part. The offline training, we use a set of grammar snippets. So we looked around buildings for some subset of the world, came up with some kind of fundamental sets of styles which seem to occur. We then devised a library of procedural building masses that could occur. We're just showing you some examples here. A library of potential roof structures, window styles, and ledges. Each one of these has a variety of parameters and designs. Then we assume a fixed camera position, and we have a sketchy style rendering you can see here on the right. So then we take each of these grammar snippets you see here, and we go through a large number of parameter values, and we create a training set. And then we train a neural network, a CNN in particular, to be able to go from a sketch to what is a probability distribution of the parameters. And then, so this is, sorry, for the type of snippet. So first we do determine which of these recognize which building style it is. And then after that, we have a parameter estimation CNN where we determine the actual parameters for that one style. And then after the deep learning part, we have a further refinement using a Monte Carlo-based optimization engine that kind of twiddles these parameter values to make the procedural model more closely resemble the sketch. And this nodes provides a considerable improvement. Here is just a video showing you a sketching process. It's sped up in 2x. So as the user sketches this portion of something, kind of a pattern is inferred, and the rest of the structure gets drawn automatically. And of course, you can just keep drawing. As you keep drawing, you just kind of refine the structure. And we added standard utilities like copy, paste, undo, and so forth. As some way of measuring the expressivity, we took the first random 20 building photos from ImageNet and from Flickr, and we just tried drawing them. So by hand, we did our best job of sketching it and showed you, it does a reasonable job of representing these structures that we saw in these 20 building photos from ImageNet. And then, as I said, 20 more from Flickr. And so this is a paper that appeared a few years ago, and there's much more information there. Next step is we said, well, what about if we don't start with a sketch, we start with a photograph? So here, from a single photograph, we want to do the same objective. So we have one photograph of a building, as you can see here, and then through a multi-stage pipeline, which includes deep learning, some optimizations, we first estimate the building mass and the camera parameters for a single picture, and then we do several refinement steps. Here we have a kind of a spectrum of building mass grammars that we support, and then facade simplification is a combination of image-based refinement and window refinement using CNNs. And then we get a facade. We have a wide range of facade grammars that are supported. And then we have a window stage. So we use a maximum vote scheme to determine a dominant window style. And again, we have a set of window grammars as well. We plug this all together, and here is a video of some example results that we get. You just select the building, you outline the silhouette, boom, press a button, and you get output like the ones you see here. And we have a bunch of these examples. We also try this with aerial pictures, not only ground level pictures. It also seems to work great. We in fact have a tool as part of another ongoing project. So we've put this online. It's called Photo to Building. And we have a recent paper in the cyber infrastructure community where we've designed a cloud computing server client interface to provide this to the public. And we've had a good number of users. So if you want to know more about this, please let me know. And finally, to conclude, the holistic aspect of urban structures, all the repetition and man-made patterns, is a beneficial thing for us to provide tools that enable us to capture the urban environments and therefore provide urban design, modeling, planning tools to help us in the problem of urbanization, which is global, which is a worldwide concern. We use in general kind of an inverse modeling methodology, which is very promising, and we will continue to do more work along this line. And many cities worldwide are increasingly interested in this. In the Wood Up effort I mentioned, there's over 100 cities there, and I've given talks in many cities around the world, and we have collaborators, and it's a very ongoing project. Of course, we look forward to even more collaboration. And of course, many thanks to the multiple funding agencies which have and are funding this work over the years. And with that, I thank you, and I believe questions will be held at a later time. Thank you.